Hi everyone, welcome to this video, Kendall Desk. Today we are going to explore some important concepts in financial mathematics, the Wiener process, least neutral measure, and Grasnoff theorems. By the ending of this video, you will understand how a Wiener process under the physical measure P is transformed into a Wiener process under the least neutral measure Q. So let's start. First, a standard Wiener process, also known as bounding motion, is a core concept in both mathematics and finance. It represents a continuous time stochastic process. Let's break down the key properties that define a standard Wiener process. First, the process starts at zero. W0 equal to 0. Second, the sample paths are continuous, which means the process evolves smoothly over time. Third, the increments of the process are stationary, meaning that the distribution of changes in the process over time depend only the length of the time interval, not the starting point. Lastly, the increments are independent. Past behavior doesn't influence future changes. This process is used to model the random motion of particles and is fundamental in the modeling of financial asset price. Next, let's talk about the least neutral measure, denoted by Q. In finance, the least neutral measure is crucial for pricing derivatives. Under this measure, the expected return of any financial asset is equal to the risk-free rate. More technically, the discounted the discounted price process, which is the asset price divided by the bond price, is a martingale under the least neutral measure. This property allows us to price options and other derivatives without worrying about investor preference. The relation between the physical measure P and the least neutral measure Q is captured by the Ladon-Nikodym derivative, which represents the change in probability between these two measures. Now, how do we switch between these two measures? That's where Grasnoff theorem comes in. Grasnoff theorem allows us to transform a Wiener process that has a drift under P, the physical measure, into a standard Wiener process under Q, the least neutral measure. The theorem gives us the conditions under which this transformation can happen. Let's consider the following. Suppose we have a standard Wiener process under P, and we apply chains of measure defined by process set T to transform it into a Wiener process under Q. The transform will follow the formula shown on the slide. Evolve and adapted process. Now, let's focus on what we are trying to prove. If we start with a standard Wiener process under the physical measure P, we want to show that under the equivalent measure Q, the transform process remains a Wiener process. More specifically, we will show that the transform process WT at the Q is normally distributed with a mean of 0 and variance t. To do this, we calculate the moment generating functions of the beauty at the Q and verify its properties. Let's begin by calculating the moment generating function of the beauty at the Q. The moment generating function helps us verify the distribution of the random variable. For constant, some constant, we define the moment generating function as m. To calculate it, we will use the Lardon-Nikodym derivative to move between the physical and least neutral measure. We substitute the expression for the beauty and the Q, which consists of the original Wiener process under P and the adapted process theta T. After simplifying the expression, we will eventually use the properties of the stochastic Ito integral to further evaluate the expectation. Now we make use of the Ito integral. This allows us to calculate the expectation in the previous expression, which will confirm the properties of the beauty and the Q. Specifically, the increments of the process will follow a normal distribution which mean zero and variance t, which brings us closer to proving that the beauty and the Q is a Wiener process under the new measures. Let's verify the beauty and the Q satisfies all the properties of a standard Wiener process. First, initial conditions. We know W 0 and the Q equal to 0, as inherits from the fact that W 0 and the P equal to 0. Next, continue as sample path. Since the sample paths of WT and the P are continuous, the same holds for WT and the Q. Stationary increment. The increments of the transform process are stationary for any s greater than 0, has a normal distribution with mean 0 and variance s. And lastly, the increment of the beauty and the Q are independent, as the process is a martingale under the Q measure. To wrap up, we began with the standard Wiener process under the physical measure P. We used Kirchhoff's theorem to transform the process into one that's a Wiener process under the least neutral measure Q. By calculating the moment generating functions and verifying its property, we show that the beauty at the Q is indeed a Wiener process under Q. This concludes our proof. I hope this video gave you a clear understanding of how stochastic processes work and the different probability measures. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more content on financial mathematics. Thanks for watching, and I will see you in the next video.